It's Sleepy Steve, helping you to fall asleep and study. Remember to subscribe to help Steve-O out, and I will keep making more sleepy stories. Now settle in gently, because tonight we are going to move in circles. Not in a worried way, not in a restless way, but in the calm and steady way that physics often asks us to move. A car rounds a bend, a ball swings on a string, a rider travels over the top of a hill, the moon falls around the earth without crashing down, a satellite quietly circles high above the clouds, moving so fast that the ground keeps curving away beneath it. Circular motion can feel strange at first because the object may keep the same speed and yet still be accelerating. So tonight, we will slow that idea down until it feels clear, soft, and manageable. Take a quiet breath in and let it out slowly. Let the room become still. Let your shoulders rest. Let the language of physics become less sharp and more like a path through the dark, where each step is simple and each idea waits patiently for the next. In the last Unit 3 episode, we looked at Newton's laws in 2 dimensions. We saw that forces are vectors, and that a net force causes acceleration in the direction of that net force. Tonight, that idea becomes especially important because circular motion is really a story about direction. An object moving in a circle is not traveling in one unchanging straight line. Its velocity is always changing direction. And because velocity is a vector, any change in direction is a change in velocity, even if the speed stays constant. This is the first big exam idea for tonight. Uniform circular motion means motion around a circular path at constant speed. The word uniform tells us that the speed is constant, but the velocity is not constant because the direction of motion is continually changing. Therefore, the object is accelerating, even though its speed may not be increasing or decreasing. In an exam, that distinction is often where marks are found. Speed is a scalar. Velocity is a vector. Constant speed does not mean constant velocity when the direction keeps changing. Imagine a small stone tied to a string being swung gently in a horizontal circle. At any instant, the stone's velocity is tangent to the circle. That means it points along the edge of the circular path in the direction the stone would travel if the string suddenly broke. But while the string remains attached, there is a force pulling the stone toward the center. That inward force changes the direction of the stone's motion again and again, keeping it on the circular path. The acceleration in uniform circular motion is called centripetal acceleration. The word centripetal means center-seeking. It is not an extra force by itself. It is the acceleration directed toward the center of the circle. The size of that acceleration depends on the speed of the object and the radius of the circle. A faster object needs a greater inward acceleration to keep turning. An object moving in a tighter circle with a smaller radius also needs a greater inward acceleration. So the formula is often written as centripetal acceleration equals speed squared divided by radius. In symbols, students usually see A equals V squared over R, but rather than rushing into the symbols, remember the meaning. Speed matters a lot because it is squared. If the speed doubles, the required centripetal acceleration becomes 4 times as large. Radius matters because a wider circle is easier to follow than a tight one. A larger radius gives a smaller centripetal acceleration for the same speed. Newton's second law then connects this acceleration to force. If an object has mass and is accelerating toward the center of the circle, there must be a net force toward the center of the circle. This is called the net centripetal force. Again, this phrase can be misleading because it does not mean there is a new mysterious force called centripetal force. It means that the forces already acting on the object must add together to produce a net inward force. In a string example, tension provides the centripetal force. In a car turning on a flat road, friction provides the centripetal force. For a satellite orbiting Earth, gravity provides the centripetal force. For a roller coaster carriage at different parts of a loop, the normal reaction force and weight may combine in different ways to create the net force toward the center. The name changes less than the question does. Always ask, what real force or combination of real forces points toward the center? This is a very strong exam habit. First, identify the center of the circle, then draw or imagine the forces. Then choose the radial direction, the direction toward the center. Then write that the net force toward the center equals mass times v squared over r. The equation is not just a calculation, it is a sentence. Net inward force equals mass times centripetal acceleration. Let us walk softly through the car example. A car turns around a flat circular bend. The center of the circular path is somewhere to the side of the car, not in front of it. The car's velocity is tangent to the curve, but the required acceleration is sideways toward the center of the bend. On a flat road, the car has weight down, normal reaction force up, and friction sideways. The vertical forces balance if the car is not moving up or down. The sideways friction is the unbalanced force that turns the car. If the car travels too fast, the required centripetal force becomes too large for the available friction. The tires can no longer provide enough sideways force, and the car may skid. This is why circular motion connects so neatly to safety. The driver might feel as though the car is being thrown outward, but the physics explanation is more precise. The car needs an inward force to follow the curved path. If there is not enough inward force, the car continues more nearly in a straight line, according to Newton's first law. That is a common misconception worth resting on for a moment. In circular motion, the real net force is inward, not outward. There may be a sensation of being pushed outward in the turning car, but in an inertial frame, the object needs an inward net force to keep changing direction. In exam language, you should be careful about saying that an object is thrown outward by an outward force. It is better to say that without sufficient inward centripetal force, the object continues tangentially or follows a path closer to a straight line. Now imagine the same car on a banked track. The road is tilted. The normal reaction force is no longer straight up. It is perpendicular to the road surface, so it points partly upward and partly inward. The inward component of the normal force can help provide the centripetal force. This is why banked roads and racetracks can allow vehicles to turn more safely at higher speeds. The banking helps direct a component of the support force toward the center of the curve. For students, banked tracks can become complicated when friction is included, but the core idea remains calm. Circular motion requires a net inward force. Banking helps by tilting the normal force so part of it points inward. If the question says friction can be ignored, then the horizontal component of the normal force provides the centripetal force, while the vertical component balances weight. If friction is involved, friction may act up or down the slope depending on whether the vehicle tends to slide inward or outward. But the center-seeking requirement never changes. Let us move now from the road to a hill where circular motion becomes vertical. A car traveling over the crest of a hill follows part of a circular path. At the top of the hill, the center of the circular path is below the car. This means the required centripetal acceleration is downward. The forces on the car are weight downward and normal reaction force upward. The net downward force is therefore weight minus normal reaction force. This explains why a person can feel lighter at the top of a hill. The seat or road pushes up with a smaller normal force than usual because some of the weight is being used in effect to provide the downward net force required for circular motion. If the car travels fast enough, the normal force can fall to zero. At that point, the car is just losing contact with the road. The condition for losing contact at the top of a hill is that gravity alone provides the required centripetal force. Now picture a vertical loop, perhaps in a roller coaster. At the bottom of the loop, the center is above the carriage, so the required net force is upward. The forces are weight downward and normal reaction force upward. To create a net upward force, the normal reaction must be greater than weight. This is why riders feel heavier at the bottom of the loop. The seat must push up strongly to both support them and change their direction upward. At the top of the loop, the center is downward, so the required net force is downward. Weight is downward, and if the carriage remains in contact with the track, the normal reaction may also point downward depending on the arrangement. The minimum speed at the top occurs when the normal force is just zero, so gravity alone provides the centripetal force. Again, this is not a trick. It is the same sentence repeated in a new setting. Net force toward the center equals mass times v squared over r. Circular motion becomes even more beautiful when we look upward. Satellites move around Earth because gravity acts as the centripetal force. A satellite in circular orbit is constantly falling toward Earth, but because it has enough sideways speed, it keeps missing Earth. The surface curves away beneath it as it falls. So an orbit is not a place where gravity disappears. It is a place where gravity is the force causing circular motion. This is another important misconception. Astronauts in orbit are not weightless because there is no gravity. Gravity is still acting on them. They feel weightless because they and the spacecraft around them are in continuous free fall. Everything is accelerating together under gravity, so there is no normal reaction force pushing up on them in the usual way. Their apparent weight is very small, even though gravitational force is still present. For a satellite in circular orbit, the gravitational force between Earth and the satellite provides the required centripetal force. This lets us connect two big areas of physics: gravity and circular motion. The gravitational force depends on the masses and the distance between their centers. The centripetal requirement depends on the satellite's mass, speed, and orbital radius. When these are matched, the satellite can maintain a circular orbit. Notice something elegant. The satellite's own mass appears in both the gravitational force and the centripetal force expression, so it cancels when solving for orbital speed. This means that, for a circular orbit at a given radius around Earth, the required orbital speed does not depend on the satellite's mass. A heavier satellite needs more gravitational force to accelerate, but it also receives more gravitational force because its mass is larger. The two effects balance. The orbital radius is measured from the center of the Earth, not from the surface. This is a common exam trap. If a satellite is a certain height above Earth's surface, the orbital radius is Earth's radius plus that height. If students use only the height above the surface, the answer can be badly wrong. So Steve's quiet exam reminder is this. For gravitational fields and satellites, always measure distance between centers of mass, unless the question specifically states otherwise. The orbital period is the time taken for one complete orbit. If a satellite travels around a circular path, the distance for one orbit is the circumference of the circle, 2 pi r. Speed is distance divided by time, so orbital speed can be related to period. A satellite with a smaller orbital radius generally has a shorter period and higher orbital speed than one farther away, because stronger gravity closer to Earth provides a larger centripetal acceleration. Geostationary satellites are a special case. They orbit above the equator with the same period as Earth's rotation, so they appear to remain above the same point on Earth. This is useful for communication and weather monitoring, but they must have a particular orbital radius to have that period. A satellite cannot be geostationary just anywhere. Its radius, speed, and period must all match the gravitational and circular motion conditions. Let us pause here and gather the formulas in words. Centripetal acceleration points toward the center. Its size increases with speed squared and decreases with radius. Net centripetal force is the net inward force required to produce that acceleration. Real forces provide it: friction, tension, gravity, normal reaction, or combinations of forces. In satellite motion, gravity provides the centripetal force. In a banked road, a component of the normal force helps provide it. In vertical circles, weight and normal reaction change their roles depending on position. When solving exam problems, the diagram is your anchor. Draw the object. Mark the center of the circular path. Draw the velocity tangent to the path if needed. Draw the acceleration toward the center. Then draw real forces only. Do not draw a separate arrow labeled centripetal force unless you are clearly using it to represent the net inward force, because centripetal force is not an extra physical interaction. It is the name for the net force requirement. A strong written response might sound like this. Although the object's speed is constant, its velocity changes because its direction changes continuously. Therefore, it has centripetal acceleration directed toward the center of the circular path. By Newton's second law, a net force toward the center is required, and in this situation, that force is provided by friction, gravity, tension, or the relevant component of the normal force. That style of answer connects vector motion, acceleration, force, and the physical source of the force. Another strong written response for satellites might say this: the satellite remains in circular orbit because gravitational attraction toward Earth provides the centripetal force required to continuously change the direction of its velocity. The satellite is not outside Earth's gravitational field. Rather, it is in free fall around Earth. Its velocity is tangential to the orbit, while its acceleration is directed toward the center of Earth. And now, as the episode settles, think again of the satellite moving silently through the night. It does not need an engine constantly pushing it forward in a circle. It needs gravity drawing it inward and enough sideways speed that it keeps falling around the curve of Earth. The motion is not magic. It is Newton's laws written across the sky. So tonight's key physics ideas are these. Uniform circular motion has constant speed but changing velocity. The acceleration is centripetal and points toward the center. A net inward force is required, but that force is provided by real interactions such as friction, tension, gravity, or normal reaction. In vertical circular motion, the direction toward the center changes with position, so the force equation must be written carefully. In satellite motion, gravity provides the centripetal force, and orbiting objects are still under gravity. Let your breathing slow again. Let the circles become quiet. Let the car turn safely on the road. Let the string hold the stone in a smooth path. Let the moon move softly around the earth, and let the satellite trace its gentle curve above the dark side of the planet. You do not need to hold every formula tightly tonight. Just remember the center. Remember that velocity points along the path, acceleration points inward, and the net force must point inward too. Sleepy Steve wishes you a great sleep. Don't study too hard. Subscribe for more sleepy stories.